Welcome, ladies and gentlemen, to our presentation Pipe Patrol, Pipeline Leak Detection using Soft Sensing Methods. My name is Daniel Vogt and I'm working now for 10 years in the field of leak detection and localization, the last 8 years together with KROHNE. My current responsibilities as a product manager include strategic product development of Pipe Patrol, the conceptual design and the planning of leak detection solutions for customers, taking into account both client and regulatory requirements. In this presentation, we start with a short introduction. Then we will explore how soft sensors can be used for leak detection. We will see an example of integration and the related results, and summarize the presentation in the conclusion. Where do we find leak detection systems such as Pipe Patrol? An example is given with a picture where we see what is called a typical chemistry-specific infrastructure for ethylene. Producers and consumers of ethylene are connected by a well-developed pipeline network. This network of transport pipelines does not only deliver the smallest CO2 footprint and is environmental friendly compared to other alternatives like trucks or railways, it also provides security of supply for all participants. And the best, it is very cost effective. This example is very well known to me for one special reason. At the moment, KROHNE's Pipe Patrol monitors all the yellow marked pipelines. In many parts of the world, major chemical sites, such as chemical parks, are connected by pipelines. And as the transported materials, such as ethylene, hydrogen or carbon monoxide, are potentially hazardous to humans and the environment, requirements regarding safety and security increase dramatically. Especially if pipelines run through urban centers including Cologne or the Ruhr area. On this slide, we show some of the major incidents with pipeline leaks in Europe in the last years. In July 2004, an explosion caused by a leak in a gas pipeline injures 132 and kills 24 people. This leak, for example, was existing for almost 14 days before the gas exploded. In March 2008, a leak in an ethylene pipeline caused a serious fire, and in March 2012, around 1 million liters of kerosene leaked out of the pipeline, because the leak remained undetected for a period of several weeks. At least 2 of these catastrophes could have been avoided by a state-of-the-art leak detection system. Another reason to operate a leak detection system may be a legal requirement like the TRFL from 2010 in Germany. TRFL is the abbreviation for Technical Rules for Pipelines, and it requires pipeline operators to install a leak detection system which uses 2 continuously operating technical processes based on different physical variables that can detect leaks in steady state, a system or process for detecting leaks during transient operating conditions, one system or a process that can detect leaks during standstill conditions, a system or process that detects gradual leaks, and a system or process for leak localization. Worldwide, this is the most stringent regulation we find related to leak detection. With Pipe Patrol, we fulfill all the requirements. We are now coming to the second part of the workshop, using soft sensors to detect leaks. Before we finally start to dive into the leak detection details, we need to specify and distinguish a sensor from a soft sensor. A sensor is a technical component that qualitatively or quantitatively measures certain physical or chemical properties in its surroundings, where a soft sensor is intelligent software that uses existing sensors to generate new information. That is why it's made up of the words software and sensor. For leak detection, there are several possibilities available. Here we want to focus on the continuously working methods on the right hand of the picture. Continuously working methods can be divided into hard sensor methods, which are also called external methods. Those methods require a dedicated leak detection sensor, which can be, for example, a fiber optic cable, an acoustic microphone, special sensor hoses, or a camera for video monitoring. The soft sensor methods, which are also called internal methods, utilize the existing instrumentation for leak detection, which is anyhow required for regular pipeline operation. The most used one worldwide is the mass balance method. In addition, we find statistical methods which try to achieve a specific confidence into the decision of an alarm. Another major group of systems use E-RTTM, the short form of real-time transient model, to calculate and consider the change of line pack in the overall mass balance. The extended real-time transient model-based systems are the latest development in this group of soft sensors and combine several of the internal methods in a unique approach into one advanced system. Traditional balancing relies on the physical principle of mass balance. No mass will be lost in a closed system. Transferred to a pipeline, the mass I inject into my pipe at the beginning should be the same mass which is delivered at the end. However, there is a fact missing in this simple equation. If we observe the blue line in the left graph, it shows the mass flow over 24 hours at the inlet of a 120 km ethylene pipeline. The green line shows the measured mass flow at the outlet for the same 24 hours. If we look at the imbalance on the right, the result is not zero, even if the pipeline has no leaks. For the period of several hours, more product is injected into the pipeline than extracted, which leads to a typical leak signature. This is possible because the gas is compressed in the pipeline. The line pack of the pipeline has increased. In traditional balancing systems, this operational signature will cause a false alarm. The only way to avoid false alarming here is to increase the detection time or the leak threshold. Both are not state-of-the-art anymore. Let's take a look at the E-RTTM method. The E-RTTM method is a two-stage system. In the first step, it uses a real-time transient model or the virtual pipeline to create the specific leak patterns. We extend it with a second stage, the leak signature analysis, a pattern recognition method, which detects leak signatures and avoids false alarming. Together, we have a unique approach, and we will look in detail how this approach is working. The first stage, to generate the specific leak patterns, in KROHNE's approach, a fully dynamic real-time process model calculates the target values. This model is based on the method of characteristics, which is considered the most accurate method for one-dimensional flow in pipelines. The real pipeline, as shown in the picture, is transferred into the computer. We consider the elevation profile, the geometry of the pipeline, the product and the material characteristics, and the thermodynamic equations of state. Based on the physical laws of conservation of momentum, mass, and energy, this leads into a virtual pipeline model which is finally driven by the online measurements. This virtual pipeline now calculates how the flow in the pipeline should be if there is no leak. The calculated flow is subsequently compared with the measured flow at inlet and outlet to create the so-called decision values. This is shown in the top graph. If there is no leak in the pipeline, calculated and measured flow will be nearly equal, and the decision values will be close to zero, as shown in the bottom graph. The operational dynamic is gone. This is why we call the RTTM a dynamic filter. If now a leak occurs, a deviation in a very specific way will become visible, a leak signature. As deviations will be created by other events as well, decision values are processed by a second stage, signature analysis. Signature analysis continuously monitors decision values for different kinds of patterns. Depending on the detected pattern, the system will suppress a message, raise a warning, or raise a leak alarm. Therefore, not any deviation will lead into an alarm, which avoids false alarming. False alarms are expensive because of shutting down the pipeline, the process, or flaring the product as a result. With this technology, false alarms are eliminated. KROHNE guarantees below 2 false alarms per year, and we have customers that have gone without false alarms for the last 10 years. Intelligent soft sensors offer additional information. Next to the detection of a leak, they can provide the localization of leaks, the calculation of line pack, provide pick and product tracking in multi-product applications, provide lifecycle monitoring of the pipeline, the calculation of the pipeline efficiency, monitoring of vapor pressure and slackline conditions along the pipeline, or alarm an overpressure violation in your pipeline. We now want to show an example of integration. So how can systems like Pipe Patrol be integrated into your environment? We already said a soft sensor is a software. This is why it typically runs on a PC, usually industrial-grade servers. It provides a flexible interface including OPC, Modbus, Profibus, or any proprietary format that can therefore be connected to any DCS or SCADA system. The field values of flow, pressure and temperature are transferred to the leak detection system. Results of the systems are given back into the SCADA system, where they are displayed in the control room environment, which the operator is used to. Of course, a dedicated HMI is available on demand, and the whole system may be laid out redundant. Leak tests were conducted on an 11 km 6-inch gas pipeline. A spontaneous leak was created 50 meters away from the inlet by opening a valve. The leak flow was led back to a flare. 3 trials have been carried out with different leak rates, 2.5%, 0.5% and 1%, based on the pipeline's nominal flow of 4,000 standard cubic meters per hour. This equals a leak rate of 120 and 40 standard cubic meters per hour. We now take a look at the flow during the course of day. The top graph shows this flow during the course of a day. It can be seen that the pipeline is operated in transient conditions in daily operations. There is no way to determine the leak dries in those values, even if we look at the standardized volume balance in the bottom graph. No leaks can be seen. The situation does not change, even if we zoom into the trial period. Both the measured values of flow meters and the volume balance hardly show any indication of a leak. The situation lights up if we look at the dynamic filter by the real-time transient model, here shown for the inlet flow value. On the top we see the inlet flow value, and we now add the calculated flow value. On the bottom graph, the decision value is presented, where we can clearly see deviations from zero due to the leak trials, at least for the 5% and the 1% leak. The 0.5% leak still is difficult to see, but it's already possible. To make it more obvious, we pass the decision values now through pattern recognition. On the top, we see the dynamic filtered value, which is also called compensated volume balance or decision value. After pattern recognition, shown on the bottom graph, the 3 leak trials can be identified clearly and easily detected by the leak detection system. To determine which sizes of leaks can be detected, it is sufficient to investigate the results of pattern recognition of a leak-free pipeline. Leak trials are not necessary. As a result, we achieve a performance plot which is always specific to the individual application. Based on this performance plot, decision can be made which detection limit and detection time is required to fulfill the individual needs. The more the parameters are chosen in the safe zone, the more safety from false alarms can be expected. For the presented application, parameters were set to a detection time of 5 minutes and the smallest detectable leak rate of 1%. To summarize, reliable leak detection is available using PipePatrol E-RTTM by KROHNE. It provides continuous and robust monitoring during all pipeline operating conditions with the help of classic sensors and instrumentation. Leak detection using soft sensors is state-of-the-art and practically accepted today everywhere in the world. In many cases, E-RTTM systems are already in use and have been certified by the Indian third-party audit like TÜV. We guarantee no false alarms and have experience in over 250 applications around the world. If you are interested in this product for a specific project or like to have more information, please do not hesitate to contact KROHNE. Thank you very much.